Hi, welcome to this video. In this video I'm going to be talking about the mathematical models that can help characterize and explain a CGM. And when I say CGM, I mean continuous glucose monitor. In fact, I do have a couple of continuous glucose monitors in front of me. This is the Abbott Freestyle Libre 2. This is some technology that ZP has, where we have something like 50 patents behind this microneedle technology. But I think the maths I'm going to talk about today is more applicable to something like a CGM, a continuous glucose monitor. Now, if you look at a CGM, I get my fingers out of the way, it actually has a very fine filament on it. And this very fine filament is actually the glucose sensor. So there is a glucose sensor that sticks out from there. And this is what I'll be modeling today. Now, the Abbott Freestyle Libre 2 is actually what they call a Generation 2 sensor. The models that I'll be dealing with and the sketches are, you could argue, are slightly more applicable to Generation 1, but I think the maths is the same, or very slight tweak to make it, let's say, applicable to Generation 2. That said, let me go forward with the slide deck. Just out of interest, Dexcom is a Generation 1 and Abbott's a Generation 2. Dexcom is also the sort of, if there's two big CGM manufacturers at the moment, it's Dexcom and Abbott, with Medtronic, who's also got a Generation 1 glucose sensor. Maybe they're in number 3, but I haven't looked at their market, how much market each one of them has at the moment. With that, let me go forward a little bit more then and say, so I'm going to be talking about a mathematical model for describing CGM, continuous glucose monitoring. So first of all, I'm going to sort of build a sketch of what the CGM is. So I'm imagining the CGM is some sort of inert, at least the start of this continuous glucose monitor is an inert material over which some insulator has been put, and then maybe there's a window within that insulator that goes back to the metal, and that window defines the area of the electrode, as I've indicated here with the arrow. So I want you to imagine that we're looking onto this electrode now, and this electrode is sitting in a solution, and this solution is, there's an electrochemically active molecule. The black arrow indicates distance from electrode. So before we turn the electrode on, and in glucose sensing, when I say turn on, it generally apply a voltage and you measure the current, and that's called amperometry. So before we turn it on, we've got all these electrochemically active molecules, but nothing's happening because we haven't applied the potential. So at T0, everything is fine. And then once we start getting away from T0, so T is greater than 0, then we will get a current. But because the term is quiescence, because we're not stirring, we're not pumping, we're not shaking, the only thing that's going on here is diffusion. So what will happen is we will start to deplete the electrochemically active molecules near the surface, and the current will fall accordingly. So we don't have a steady state current, we have a current that's falling as the square root of time. This square root of time, the equation that sort of defines this falling current, they call it the Cottrell equation in electrochemistry. It's really a derivative of Fick's laws of diffusion. But I'm going to describe for CGM, there's a better scenario. In fact, CGMs tend to act more like steady state systems. So at the moment I've got this bare electrode, and if I don't stir the solution, then the current falls as a function of time. But if I do have a magnetic stirrer in there and I stir that solution, in fact the current now stays steady state. If everything else is constant, so when I say everything else is constant, not glucose necessarily, but the electrochemically active molecule is constant, then the current is constant. And if that is the situation, if you do have stirring going on and your current is constant, because the concentration of the electrochemically active molecule is also constant, then you can define that current as I is equal to N, which is number of electrons, F, which is Faraday's constant, is the charge associated with a mole of material. I'm a chemist, this term mole is, I appreciate it can be quite confusing for people. A is area of electrodes, so this is something that you manufacture. So when you're making CGMs, you would control on A. You can't really control on N. N is the number of electrons. That molecule is going to give you those electrons, and you've got to really know sort of take on it. F is a sort of a universal constant. You're not going to be able to, let's say, do anything about it. A is something that you manufacture. Now mass transport here, this km here is really defining. It's really, when you look at its units, it's almost velocity. So if you stir fast, then current is going to be faster. If you stir slow, current will be less. If you're flowing fast, current will be higher. If you're flowing slowly, current will be lower. So km is a mass transport constant. And then I've got C, which is the concentration of the electrochemically active molecule. So in my steady state condition where I am stirring, the current that I'm looking at is equal to, the current is proportional to N. There's nothing you could do about N. That's just defined by the chemistry that you have. F, there's nothing you could do about Faraday's constant. It's the charge per moles. A is something that you manufacture. Km is kind of an experimental setup. So if you're setting this up, if you stir at different speeds on different days, you will essentially mess up km, or you will change km. So you probably want to keep that fairly constant. And then C is the concentration of the molecule that you put in there. So you control that. So this I'm here is defining a bare electrode where there's some sort of forced mass flow, stirring, shaking, flowing, whatever. And then the current then is proportional to N and F. So N you can't do anything about, F you can't do anything about, A you control, Km is how much you're flowing or stirring, and C is how much of that electrochemically active molecule do you actually have in that solution. If you cancel out all the units, you will find yourself that on the left hand side we have current, which is amps, or you can call it charge per second. And if you cancel out all the units on the right hand side, you're going to find out you end up with charge per second or amps. So you can at least check this equation is fine just by balancing the units or cancelling out the units. I'm going to define now a slightly different scenario now where we took our bare electrode and we put a membrane over it. I'm not going to stir this time, but I'm going to show you a slightly different scenario that we have our electrode, we have a distance from our electrode, but we've got a membrane in front of it. By putting that membrane in front of it, what happens is not all those electrochemically active molecules can get to that surface. They're actually blocked or filtered, let's say, by the membrane. So you've got actually quite a lot of material just outside the membrane, but only a few molecules actually get into the membrane. So this actually ends up setting up a steady state condition as well. So at t is equal to 0, nothing's really happening. But then when we go to greater than t is equal to 0, we don't get this current falling as a function of time, because in fact there's a large reservoir just on the outside of this membrane that's able to replenish every time we oxidize, for example, a molecule. So in fact the current ends up being, it's less than the bare electrode, but it's less, and it remains steady state. Now in this situation, current is proportional to N, F, A, Km. I'm just going to get myself to disappear out of the image. N, F, A, Km, C. That's the same equation that I actually used earlier on, but I just want to explain that Km now means something slightly different here. So we've got current, N is number of electrons, F is Faraday's constant, A is area of electrode, that's what you're kind of essentially manufacturing, or you have manufacturing control on. Km doesn't mean the same thing now. This is not kind of how fast you're stirring or how fast you're pumping or how fast you're shaking. I'll come back to that in a minute. C is the concentration. I don't know why I put Cm in there, that's a typo, but that should be just C. So Km in this point actually means there's something slightly different. It means the effective diffusion of my molecule through that membrane divided by the thickness of that membrane. So now you can understand you've actually got a handle on Km, because you've got, I'll just click one more time. So D here is the thickness of the membrane here. So if you make a membrane that's thin, Km is essentially bigger. And if you make a membrane that is thick, Km is essentially smaller. So you can see that you've got a handle on controlling current through just the thickness of the membrane. But this D effective is sort of telling you about the interaction between your molecule and your membrane. If you make a membrane that is very dense, then D effective will be lower. If you make a membrane that's very porous, the D effective will be higher. So I can essentially tell you that Km in the first example, when we had a bare electrode, sort of meant mass transport. It still means mass transport in this one, but it really means mass transport across a membrane. And you can see now that you've got sort of a physical handle on this, which is how thick you actually made that membrane. Now, bringing this slightly closer now to an actual glucose sensor. In a glucose sensor, you can end up with an electrode. You'll put an enzyme layer on it, and you'll put a barrier layer on it. Now, on the previous slide where I had that membrane in place, I was really sort of describing the barrier layer situation, but now I'm adding an extra layer, which is the enzyme layer. I don't want to preach about or be pedantic about the reaction here, but we have glucose, for example, in a CGM that's mostly repelled by the barrier layer, but some of it gets through to the enzyme layer. And then we have a specific reaction where glucose is reacting with the enzyme, and we end up generating hydrogen peroxide because oxygen reacts with the enzyme and generates hydrogen peroxide. And that is what is then oxidized on the electrode. It's with what you try to do is in this is set the reaction up in such a way that in fact the limiting factor here is glucose itself. Nothing else is limiting. And if you set that up correctly, then what you will end up doing is you will end up with a concentration of hydrogen peroxide is really just equal to a sort of constant times glucose. So when I say constant, maybe I should use the term efficiency here. So, for example, the detectable hydrogen peroxide concentration may be only 10% of the glucose concentration on the outside of the sensor. So K is a kind of coefficient, maybe between 0 and 1, whereas 0 means that there's really no reaction going on and basically you have no hydrogen peroxide, and 1 means that all the glucose becomes hydrogen peroxide. Well, that's not really the case. It's more likely to be more like 10%, but that's a bit of an opinion from me based on based on experience, but it will really depend on how you set up the barrier layer, for example, what that real K value is. But K is probably taking a value between, is taking a value between 0 and 1, and it's a way of saying, in fact, on a glucose sensor, I want to use, in the end, it's actually the hydrogen peroxide that I'm actually detecting, not the glucose, and the connection between hydrogen peroxide and glucose is actually this sort of K value, and you can think of it as like an efficiency. With that said, I'll be using that in a minute. So I take my bare electrode, I put my membrane on there. Maybe I should say I put my enzyme layer down, I put my membrane back on top, and now my current is proportional to N. There's nothing you can do about N. F, Faraday's constant. A, something that you manufacture. Km at this point is something that you manufacture. It's how you make that polymer and how thick you make that polymer. C is really is a concentration, but in this case now it's almost like the glucose concentration times this K factor here, which I say takes a value between 0 and 1. And so if you're actually doing a CGM experiment, this is one way of doing a CGM experiment. You've set up your formulation on your sensor. You've put your sensor into a beaker. First of all, you have no glucose in there. And then you record the current, so that's your kind of background current. And then you add glucose and the signal goes up, and you record your new plateau current. Then you add some more glucose and then you record your new plateau current. Just notice that these currents are actually steady state. Then you add some more glucose and the current comes up. And you end up plotting a whole series of currents versus concentration. And you can give that a slope. I can give it a slope, call it sensitivity if you want, but maybe you'll end up with a slope with nanoamps per millimolar. Now, when you look at that slope, when we look at our equation earlier on, I is equal to NFAKM, K glucose times concentration of glucose. When you look at that equation, all those terms are actually tied up in S. So, you can almost say that current is proportional to slope times glucose concentration. There's also probably an offset due to you didn't get zero current at zero glucose concentration. but it's just to say all those terms are actually tied up in that S value. So as I say, let me, if this video is interesting, that's great. If you're interested in CGM, obviously reach out to us at ZP. I mean, when I say reach out to us, we're really contract developers, contract manufacturers of CGM technologies, including we are the owner of the IP behind this microneedles watch, and we use this microneedle technology in the CGM space, and it's something that we license and we do programs with well-funded clients to actually get that technology to market. But if you have any questions, as I say, don't hesitate to reach out to us. Okay, thanks very much.